And having taken the case of electrostatics, we have gone on to understand what is the finite elements method, how to use the finite elements method to an electrostatic, to the solution of an electrostatic problem, which essentially means solution of the Laplace or Poisson's equation. Now what I'm going to do is I need to go forward and see how I can modify. So all of you by this time have written the MATLAB program to solve the electrostatic equation, electrostatic fields using the finite elements method. Now we need to understand how to extend whatever we have learned so far to non-electrostatic fields, or rather other fields, electric and magnetic fields, which we encounter in electrical engineering. So for that, what I'm going to do is I'm going to take the next logical step. After having worked with electrostatics, I'm going to talk about magnetostatics. And before I apply magnetostatics to a finite element to magnetostatics, what I'm going to do is I'm going to do a brief overview of the basics of magnetostatic fields, in which I will also talk a little about what we have covered. So you will see that electrostatic fields and magnetostatic fields are analogous fields, and therefore you almost have situations corresponding to each other, and this will help you understand the generality of fields. I mean, how the fields are kind of similar, and how to work with fields such that you can use the same program that you have written with modifications to apply to other kinds of fields. So today we are going to talk about static fields. We're not going to talk about finite element method, but I am going to talk about this from the perspective that we are interested in using this. We are ultimately interested in using the finite element method for electrostatic or magnetostatic fields. So now we know that the first thing, whenever we encounter a particular kind of field, what we need to understand is what is the kind of equation. We need a partial differential equation. This much we understand by this time, that the finite element method can only be applied to a partial differential equation. This is not entirely true, but that we will discuss later. So therefore, whenever you have a field, the first thing is to identify the partial differential equation that needs to be solved. There is also another reason why I am starting from this perspective. You have already been introduced to COMSOL in the previous yesterday, and you will see that COMSOL allows you to solve electrostatic, magnetostatics by name, but it also gives you the option to choose whichever partial differential equation you wish to solve. So you can take your own partial differential equation and you can solve it using COMSOL. If you know how to frame the partial differential equation, even when a user-friendly GUI is not given. And the same holds for your the codes, the MATLAB codes that you have written yourself. Whatever you have written, right now it solves Poisson's equation. Ultimately, what it should be able to solve is any partial differential equation. I should be able to specify the partial differential equation I want to solve, and you should be able to, your program should be able to tackle that. But that comes later. Right now, let us concentrate on electrostatics and magnetostatics. So you have seen that in electrostatics, the partial differential equation that you work with is the Poisson's equation, which can be written as minus divergence of epsilon naught epsilon r grad phi is equal to rho. Or you can write it in the, okay. Now, if you look at this equation carefully, this is the partial differential equation. Now, what do we need to know? We need to know the material parameters. And embedded in this equation are certain quantities which are material parameters. One of them is permittivity of free space. That's not a material parameter, but that is the permittivity of vacuum. When you work with a material, you have epsilon r, which is a material parameter. It is a scalar quantity because we are going to consider in this course only isotropic and homogeneous material, but it can also be anisotropic. If it were anisotropic, it would have to be represented by a tensor. This is not something that I am going to cover in this course, but you can take it up for your term paper. And then there is another thing, that is volume density, rho. The volume charge density is not a material parameter in the sense that it is, it is not really, I mean, as soon as you know the material, you do not know the charge density. But I have told you that in finite element method, we make the assumption that within an element, the space charge density is constant. This is, of course, actually a forcing function, so a source function, which has to be specified for a particular problem. But the moment you define an element, you define the material parameter, you also define the space charge density. You're not allowed to allow, I mean, if the space charge density changes within a element, then you have to break it up into two elements. So these are the two parameters, epsilon and rho, which need to be specified. We have a third parameter, which is P, and P is a polarization vector, much in the nature of electric field intensity or electric flux density D. So just as D at a point is defined by dx dy dz, similarly P is defined as px py pz, and the difference between D and P is that P describes a volume density of bound charges. And by this time, you're well aware where these bound charges come from. But I will still go through for the sake of completeness. Most of you have, I think, oh no, we did not discuss polarization, or did we, in the course? Never mind. I can describe it again. So the point is that polarization vector describes the volume density of bound charges. Rho describes the volume density of free charges. Permittivity takes into account the effect of bound charges. So as I have mentioned to you before, you do not need to account for P and epsilon naught together. You choose one or the other. In fact, I think this question came up in the interaction with Professor Raju as well. As engineers, we are interested in the net effect, so we are interested in permittivity. However, if you are designing a new material, for example, when we work with nanodielectrics, in that situation, P might be important. So to quickly go through polarization, I have discussed this before in 634 also. When you have a dielectric and there are already dipoles within the material, or in case of polar substances, or in case of non-polar substances, dipoles are set up within the material. How are dipoles set up? I'm not going to go into that discussion. We have discussed that earlier in 634. We have various kinds of polarization mechanisms. We have atomic dipoles, where you have effective charge separation between the charge center of the nucleus, which is positive, and the charge center of the electronic cloud, which is negative. When you apply an electric field, these charge centers separate out and a dipole is created. If you have anions and cations in a molecule, these positive charges and negative charges will move in the direction of the applied field, and there will be an effective charge separation. If you have polar materials, you already have dipoles within the material, but they are aligned in random directions, and therefore the net dipole moment of the substance is zero. However, under the application of the applied electric field, these dipoles will orient themselves in the direction of the field, and you will have a net dipolar polarization or orientational polarization. Then there are other kinds of polarization mechanisms also, which are low frequency mechanisms. So I'm not going to cover them in this course. So these dipoles will align themselves to the direction of the field. Now, if you look at this positive and this negative cancel each other locally. This positive, negative cancel each other. So you're left with a surfeit of positive charges near the negative electrode and a surfeit of negative charges near the positive electrode. So you can imagine that there is a induced electric field, which is in a direction opposite to the applied electric field. As a result, if you look inside the material, if you're inside the material, you will see a field which is lower than the applied electric field. And therefore, you will be able to probably withstand more dielectric strength. So that is the nature of dielectric materials over and above vacuum. Vacuum does not have polarizable dipoles. So polarization, therefore, depends upon the number of bound charges and therefore can be represented as the total polarization P can be written as Q into L into V. This is the dipole moment, the total effective dipole moment, which can again be written as Q by A, which is equal to rho SP. So therefore, this is polarization charge density. And P can also be written as the limit. So remember, we are interested in defining every quantity as a point function. We've done that for D, done that for E, done that for rho. Similarly, P can be written as limit delta P delta V, so the total polarization within a unit volume in the limit that in volume tends to zero. So the total polarization moment in an infinitesimal volume gives you the polarization at that point. If you consider a linear dielectric, then the polarization is dependent on the applied electric field E. And the direction is also the same. So therefore, P is equal to epsilon naught xi E, E. So P and E are vectors both in the same direction. Xi E is the electric susceptibility of the material. And I have shown you in the previous 634 epsilon therefore can be written as epsilon. No, I have shown this in the previous lecture on electrostatics. Epsilon is equal to epsilon naught 1 plus xi e, which means 1 plus xi e is nothing but epsilon r, which is the dielectric constant of a material. So therefore, the important thing is that we can write this relationship D is equal to epsilon naught E plus P. D, E, and P are vectors all in the same direction, and epsilon naught is the permittivity of free space. So this is a relationship that we often use. This is called a constitutive relationship. And then you have the boundary condition. Boundary conditions, again, I have discussed earlier, are of two types. Either you have Dirichlet boundary condition or Neumann boundary condition. For an electrostatic problem, the Dirichlet boundary condition means that the potential needs to be specified because you're solving for the potential, electric potential, and therefore it must be specified at a given boundary. So phi is equal to phi naught, phi is equal to 0. So 0 non-zero values, at any boundary, it has to be specified. So that is the Dirichlet boundary condition in an electrostatic field problem. Additionally, you can have Neumann boundary condition where you have the flux density specified, that is rate of change of the potential. Ordinarily, we would have n dot d is equal to 0, but if there is surface charge at a boundary, then n dot d is equal to rho s, and the surface charge density would be an input condition to your problem. It has to be specified. Unless you do that, you cannot solve the problem. As you are well aware, right away that we discuss partial differential equation, we also have to discuss the concomitant boundary conditions, because without the boundary conditions, you cannot obtain a unique solution. So either it's a Dirichlet boundary condition or a Neumann boundary condition, which you need to specify. Now, if you apply this to the case of conductors, we are concerned with the electron mobility. We are not going to talk about hole mobility here because we are talking about conductors, but in dielectrics, we might also be interested in hole mobility, but we are not going to go there now. Electron mobility is defined as minus mu EE. So it is again proportional to the electric field intensity. Additionally, you will have a current which is caused by this mobility, and this current density is given as rho V into U. So therefore, this is a volume charge density and this is the mobility. So if you're talking about electrons, we are talking about mobility of the electrons. And therefore, from this, you have the conductivity of the material, which is given as minus rho V mu E, which is again Ne mu E. N is the number density of electrons, mu E is the mobility of the electrons, E is the electronic charge. So therefore, the conductivity of a material is related to the electronic charge if you're considering only electronic current, number density, and the mobility. And this brings us to the point form of Ohm's law, which holds for conductors, that is J is equal to sigma E. So J is equal to, if you put this relationship here, J is equal to sigma E, you can obtain by putting the relation of mu E in place of rho U here. You will get the relationship J is equal to sigma E, where sigma is given by Ne mu E. This is actually true for both dielectrics and conductors. If you had a perfect dielectric, you would have zero current density, which would give you J is equal to 0, and you would be fine. But in reality, of course, there are no perfect dielectrics, and therefore, even in dielectrics, you might be called upon to solve for the current density. You might need to find the current density even in a dielectric. For a perfect conductor, E is supposed to be 0. Again, that does not hold true, and you may have to solve for the electric field distribution in a conductor. I again stress that when we are talking about circuit models, we don't bother with the electric field distribution, because in circuits, we are taking a particular conductor shape and configuration, and we assume that the current density is constant throughout the area of the conductor. We can consider thin wires, and we consider only potential difference, so E is equal to V by D. But that need not be true for a conductor which is not necessarily a thin wire conductor. So in that kind of a situation, you would have to compute the electric field with electric field distribution within the conductor. You would be able to compute the current density within the conductor, and it depends on whether it is necessary or not. So therefore, even when we are talking about conductors, we need to know how to frame the partial differential equation. So this is all about conductors. I'm not going to read that. You have a test charge. If it's a conductor, it is free to move. Therefore, it experiences force. Therefore, it has drift velocity. It has mobility. And therefore, you have conduction current. So if that is the case, that if you have conduction current, what would be the fill like? Again, here I'm taking a trivial situation just for the sake of explanation. You have, let's say, two conductors, and you have a conductor in between, which is not a perfect conductor, so that it is able to hold a potential difference. So let's say the potential difference is phi is equal to phi A, and on the top conductor, and phi equal to phi B on that bottom conductor. And you have a material with conductivity sigma 1. There would be, therefore, a current density within this conductor material. Now, from the look of this, it looks like this is a trivial problem, but I'm only using it as an example to set up the equations. If it were not so nice ideal parallel plates, and let's say you have a ragged surface, in that case, you would have to compute the field distribution and the current density, which would be space dependent. How do you do that? So even in this region, you have these equations which hold. E is equal to minus grad phi. That is always true. And if you assume that there is no charge accumulation, then divergence of J is equal to 0, that is KCl. So at any point within this material, whatever is the current density flowing in, the same current density should flow out, and there should be no accumulation of charge unless otherwise specified. And then you have the relationship J is equal to sigma E, which is your constitutive relation. So you see, you have three relations analogous to the dielectric situation. In fact, the first two, this equation is the same. Instead of divergence D is equal to rho, you have divergence J is equal to 0. Instead of D is equal to epsilon E, you have J is equal to sigma E. Now, when you put these three equations together, you have what is called the Poisson's equation or Laplace's equation for conductors. Divergence of J, in place of J, you put sigma E, therefore divergence of sigma E is equal to 0. If you consider sigma to be constant within the material, isotropic homogeneous material, you can take it out, so you have divergence of sigma minus grad phi is equal to 0. And this is nothing but Laplace's equation, except that instead of permittivity, you have conductivity. Now, in case of conductors, you might have a situation where over and above a potential difference that establishes a current through the material, there might be an external source of current. Let us imagine that there is an external source of current, which is J naught. In that case, the total current density would be J plus J naught. And if there is no accumulation, if there is an accumulation of charge, then divergence of J is equal to Q. So at any point, Q quantity of charge may be established. So if you modify the two equations, this particular equation and the total current is different. In that case, in the presence of an external current, and if there is some amount of charge accumulation or current accumulation, your equation is modified with a non-zero term on the right-hand side. So in that case, you have minus divergence of sigma grad phi is equal to Q. This is now analogous to Laplace's equation. So it is not necessary that you have to have an external current. Having an external current is analogous to the situation where you have polarization, and having charge accumulation is analogous to the situation where you have charge density, charge presence within volume charge density within the dielectric. Similarly, if you have charge accumulation due to a disparity between the current inflow and current outflow at a point, you would have a non-zero right-hand term. You already know how to deal with this. This will contribute to your force vector, and as before, you will be able to obtain the stiffness vector. So therefore, what it means is, at the moment, you know how to solve or how to modify your existing program to solve for electric fields within conductors. So far, what have you done? You have written the program to solve for electric fields within a dielectric material only, for an ideal parallel plate capacitor. That same program, now you can make very small changes and you can use it to apply to conductors. You will have to use conductivity, you will have to use Q, and whatever else you have done will hold. You do not really need to make any other changes. Of course, we also have to look at the boundary conditions, because no PDE can be solved without the proper boundary conditions. So even in this case, the first thing that we need to look for are the Dirichlet boundary conditions. Remember, here again, we are solving for phi. So phi is our variable, which is the potential, and therefore the Dirichlet boundary condition means that potential has to be specified. So you have identical potential, identical Dirichlet conditions. You have potential difference between 2 points or 2 boundaries, phi equal to 0, phi equal to some value. But what happens to the Neumann boundary conditions? Neumann boundary conditions ordinarily would be n dot j is equal to 0. What does this mean? It means that there is zero current flux. At a particular point on a boundary, there is zero current flux. That is, there is no net flux flowing out, no normal net flux flowing out of a boundary. And this is equivalent to an insulation or symmetric condition. The reason that I am bringing up these terms now here are, when you use a finite element program, you will not be asked to specify zero current flux. You will be asked to specify whether a boundary is an insulation boundary or a symmetry boundary. I want one of you to answer that. What does zero current flux mean? What does insulation or symmetry boundary condition mean at a boundary? So if I say that at a particular boundary, you have a symmetry boundary condition or you have an insulation boundary condition, what am I physically saying? Mathematically, it means that n dot j is equal to 0. What does it physically mean? Who will answer?
And there is no fringing at the
fringing. We are not talking about electric fields here. We are talking about currents. See, that is the analogy. See, in case of dielectrics, this corresponding equation is n dot d, which means that there is no flux density crossing a boundary, which means there is no fringing, which means the flux density is parallel to the boundary. But here we are talking about currents.
Ma'am, the current is perpendicular to the plane.
Balaji. Perpendicular?
Perpendicular, because n dot j is equal to 0. So
0, it's 0.
Yeah, so
normal. J normal.
Sorry, tangential.
Tangential, yes.
Tangential.
Yeah, the normal is 0, so tangential exists. No, but how does this physically signify insulation or symmetry?
Ma'am, suppose we have like a conductor, and on top of that we have insulation, means the cable.
Yeah, let's say it's a
example
perfect
of cable.
insulator. Yeah.
So for perfect insulator, the current won't pass out of the
Yeah, there will be no component of current
boundary,
which is flowing into the insulator.
But if the insulator is non-ideal, then there will be some current passing from the live conductor to the ground.
Sure. So insulation means, when you say that you have insulation boundary condition at a boundary, it means that you have the presence of a perfect insulator there. The current is completely constrained at that boundary. And you have to use the same condition for symmetry. So we will talk about symmetry later. Symmetry means you are perfectly, I mean, there is nothing that is going out. And then this is, of course, the homogeneous Neumann boundary condition. Similarly, you have a specified Neumann boundary condition, which is n dot j is equal to minus del rho s del t, which means that there is some current, and this current is causing charge accumulation at a boundary. Do you understand this? So this means that at a surface, there is a component of current. There is some amount of normal component of current. And since this is a boundary, we are not interested at the moment in what is happening across the boundary. As far as we can see, what is happening is that because of a current flow at the boundary, there are some surface charges which are accumulating at the boundary. Accumulation of surface charges, and remember, when we talk about surface charges, we're again talking about free surface charges. So whenever we talk about accumulation of surface charges at a boundary, essentially what would happen if over a long period of time, charges accumulate at a boundary? What would be the consequence of that? The voltage at that boundary will increase.
The voltage will raise if it is a positive charge.
That's right. That's right. So we are talking about a voltage being given to that boundary. And if you need to solve the problem in this kind of a situation, remember, this again contributes the forcing function in the right-hand side. So we need to know the value. We need to know this flux. We need to know the value of the current flux. Otherwise, we cannot solve the problem. So these are your boundary conditions, Dirichlet and Neumann boundary conditions for the Laplace's or Poisson's equations as applicable applied to conductors. Now I need to go on to
one thing I want to clarify.
Yes.
The first term, like if it is non-zero, then can we compare that situation with the transmission line, means charging of transmission line?
Yes, you can.
Yes,
yes, in a way you can. Yes. Yeah, I understand. The charge is accumulating on the transmission line. That's charging. Capacitive charging.
Yes, ma'am. If we open the line through the isolator, then also there is some charge. Then we need to discharge that line.
Yeah, and that will result in a voltage rise. Yes, you can.
Okay.
Okay, so let me talk a little bit about vector fields in general terms. Again, this is something that you have done in your UG, but let's go through it once more. So any vector fields, you have scalar fields and vector fields. Scalar field is your electrostatic field, let's say. But any scalar fields or any vector fields can be uniquely defined by its divergence and curl. So here I have 4 different kinds of vector fields. Look at the first vector field. Let us imagine that it is all these are vector fields in an arbitrary quantity A. A is a vector. Look at the first figure. What is the divergence of A in this field?
Not 0.
0. What is the curl?
Curl will be 0.
Curl is 0. So the moment I tell you that I have a field which has 0 divergence and 0 curl, you know that this is how the field lines look like. Then we come to the second case. In this case, what is the value of curl?
Curl will be 0.
Curl will be 0. There is no curl. Divergence?
Divergence will be positive.
Divergence will be positive. So there is a source. There is a source of fields in this at this point. So I am immediately being able to specify the field distribution around that point. So this is the second case where divergence of A is not equal to 0 and curl of A is equal to 0. What kind of field does this remind you of?
Charge, positive charge. And
electrostatic field.
Electrostatic
field, yes. Look at this field. What is the divergence of this field? What is the curl of this field?
Some divergence will be 0 And
Divergence is 0. Curl
curl
is
will be inside the
non-zero.
page. Inside the page. Yes.
Yeah, that's a finite quantity. So therefore, in this case, you have a field which whatever is going in is coming out, but it has a curl, it has a rotational. What kind of field does this remind you of?
Ma'am, this is a magnetic field for a current carrying conductor.
Magnetostatic field.
Yes, ma'am, magnetostatic field.
A magnetic field which is not changing with time.
Yes, ma'am.
That is a current carrying conductor, which means a steady current. Yes. And then you come to the last kind of field. Here you can see the divergence is non-zero as well as curl is non-zero. So what I'm trying to tell you is that a field can be uniquely defined. Its property can be uniquely characterized by its divergence and divergence and curl. When we are talking about divergence, we are specifying the outwards flux per unit volume as the volume around that point shrinks to 0. So we are thinking about an infinitesimal volume around a particular point and the outward flux per unit volume for that volume in terms of Gauss's law. So that is how we write this. Divergence of A is equal to integral A dot ds divided by grad V in the limit delta V tending to 0. Remember, Q, the total charge is integration A dot ds. I mean, this is A is not necessarily the electric field, but whatever field it is. And the curl is the rotational vector whose magnitude gives you the maximum circulation of A per unit area as the area tends to 0. So you think about a point here, and then you will have to imagine a unit area normal to the point, normal to the direction of the field at that point. And then the curl at that point tells you what is the maximum circulation of A per unit area in the limit area tending to 0. Now, why am I talking about all these various different kinds of fields? The reason is this. Let us imagine you have a field which has divergence equal to 0. Let's say you have divergence of A is equal to 0. Such a field is called a divergence-less field or a solenoidal field, which means that flux lines of A entering into a closed circuit must also leave it. All the flux lines that are entering into a closed surface will also leave that surface. So that is a divergence-less field. Now, if you have a divergence-less field, you should be, by vector identity, you should be able to express that field A as the curl of a second arbitrary vector. So if divergence of A is equal to 0, it means that it is possible to express A as curl of F, where F is another arbitrary vector. Because why can I write this? Because the divergence of the curl of any vector is 0. That is why I can write this. Similarly, the other kind of field that you have is where you have curl equal to 0 instead of divergence being equal to 0. So when you have curl A is equal to 0, we call that means rotation is 0. Therefore, we call it an irrotational field. So you can have two kinds of fields, a solenoidal field and an irrotational field. In an irrotational field, circulation of A around a closed path is 0. Whenever you have an irrotational field, whenever you can express the curl of a vector to be 0, that vector can be expressed as the gradient of a scalar quantity. So therefore, any irrotational field A can be expressed in terms of a scalar field V. I am writing V because I want to distinguish V from the vector field F, and also because what is the irrotational field that comes to your mind immediately?
Ma'am, DC current flowing through a conductor. Because if it's AC, then there may be the stray currents.
If you have a DC current flowing through a conductor, you'll have
Yes,
a
sir.
magnetostatic field. We have just discussed that.
No. There will be, the current will be irrotational. J will be irrotational.
J is not filled. J is current density. Whenever you have J, you have magnetostatic field. There's nothing you can do about it. You learned it in class 8 maybe. DC currents, when you have magnetostatic field. You do not have electromagnetic field, but you have magnetostatic fields. Can you think of an
I'm just
irrotational field?
giving the example of the irrotational. J is also a field for J vector. It will be also a field now.
What is
At
the
the
equation you're
cross-section.
talking about? So I need to have an equation, partial differential equation in J. Why are you going there? You're missing an obvious point. What about the rest? Have you people gone to sleep?
Electric field.
Electric fields. See, the hint is there. I was trying to tell you why I have used grad V and not grad XYZ. Your electric field E is
Yes,
an
ma'am.
irrotational field because curl of E is what?
Yeah, ma'am. If magnetic field is not changing, then curl of E will be 0. If it is changing, then it will be non-zero.
We are not talking about magnetic fields. We're talking about electrostatic fields.
Yes, ma'am.
The electrostatic field that we have been discussing for 1.5 months or more, for half the semester. We've been talking about electrostatic fields. I'm just looking at electrostatic field in a different way. The electrostatic field satisfies this equation. Curl of A is equal to 0. That means I can write A as equal to E. Curl of E is equal to 0. And if curl of E is equal to 0, E can be expressed as the gradient of a vector. E is minus grad V. So that is why I have suddenly brought V here, because whenever you talk about an irrotational field, and you are aware that an irrotational field can be expressed in the terms of a scalar field, the field that you think about is your potential field. So this is your electric scalar potential. So therefore, an irrotational field is a conservative field. Line integral of A is independent of the chosen path and is identically 0. Now you need to understand that this V is a scalar quantity, and therefore V is a scalar potential of E. Whereas, okay, I'll come to the non-scalar vector potential later. So far we have talked only about E, and therefore we see that because E is an irrotational field, I can express it in terms of a scalar potential of E, and that is what we have done so far. Now I want to come to magnetostatics. Oh, okay, there's something more before that. Now, let us imagine a situation where so far we have considered cases where either the divergence is 0 or the curl is 0. If you have a fictitious field, we will keep it fictitious at the moment because I'm going to use it to discuss certain things later. We are not going to discuss anything other than electric and magnetic fields. If let's say you have a field, which is this field, last field, where you see that neither is the divergence 0 nor is the curl 0. In that case, we consider some non-zero values. Let's say divergence of A is rho V and curl of A is rho S. This does not have any physical significance at this moment because we are talking about fictitious fields, but I will call it the source density rho V and I will call rho S as the circulation density. You will understand intuitively why I am doing this. Are Baba. Why I am doing this? See, think about the analogy of divergence of E is equal to rho. So whenever you have a non-zero divergence in a field that you know, which is your electrostatic field, it is because of the volume charge density at that point, and the charge density in an electrostatic field is also the source density. A charge is the source of electrostatic field. So by analogy, no matter what the field A stands for, if it has a non-zero divergence, then that quantity, that finite non-zero divergence, can be considered to be the source density rho v. Similarly, curl of A is equal to rho s is the circulation density. We will see later. You actually know why this is circulation density because you are familiar with magnetostatic fields, but we will see about that later. Now, Helmholtz theorem tells us that for any vector that satisfies the above equations, and if with both densities vanishing at infinity. So the source density is present within a finite volume, but at infinity there is no source. Similarly, the circulation density also vanishes at infinity. In such a situation, what you can do is you can take this you can take this arbitrary field A, which has a non-zero divergence as well as a non-zero circulation, and you can express it as the sum total of two separate vector fields, AI and AS. And AI is the irrotational part, and AS is the solenoidal part. So what I'm doing is I'm taking my arbitrary vector field A, and I am trying to express it mathematically as the superposition of two vector fields, AI and AS. One of them is irrotational, which means that curl of AI is equal to 0. Curl of A is not equal to 0, but curl of AI is equal to 0. And the second component is the solenoidal field, which is divergence-less. Therefore, divergence of AS is equal to 0. Divergence of A as a whole is not 0, but divergence of AS is equal to 0. If this is true, now if AI is irrotational, AI can be expressed as minus grad V, and AS can be expressed as the curl of a second arbitrary vector F, which means the vector field A can therefore be written as the sum total of two vectors. One is the gradient of a scalar and the other is the curl of a vector. Now, please note that we are taking this minus sign. While talking about E field, you know why we take this minus sign. A similar situation holds, that is arbitrarily chosen. So this is a situation that we might encounter in future. When we encounter that, we will look at it. So what I'm saying is that, as you can see, this is a scalar potential. This F, which is, when you have a solenoidal field, that solenoidal field can be expressed as the curl of a vector F. This F is called the vector potential. So therefore, whenever you have an irrotational field, it can be expressed in terms of the scalar potential. And whenever you have a solenoidal field, it can be expressed in terms of a vector potential F. And if you have non-zero divergence as well as non-zero curl, then that can be expressed in terms of that particular field A, can be expressed in terms of two potentials. One is a scalar potential and the other is a vector potential. Is this point clear to everybody? Yes or no, Baba?
Yes, ma'am.
Okay. Then you define what is called the Laplacian. Laplacian is nothing but the divergence of the gradient of a potential. So that is del square v del x square. We've already done this, del square v del x square plus del square v del y square, etc. So the Laplacian operator is this operator. For a vector, of course, you would have three components, ax, ay, az. And in that situation, this becomes equal to, by identity, it is the gradient of the divergence of A minus curl of A. If you take this, you will be able to find this. So the Laplacian for a vector field and the Laplacian for a scalar field are different. Now let us come to magnetostatics. So far we have been discussing some general things about fields. Now I will come on to magnetostatics. When do you have magnetostatic fields? Whenever you have a steady electric current. So when you have a stationary charge, you have an electrostatic field. As soon as the stationary charge begins to move, and Hitesh, as you talked about DC fields, that means a constant current, steady current, you have magnetic fields. Now magnetic materials are characterized by permeability. And what is the relationship? You have seen, we are going to set up analogous equations. So when you talk about magnetic fields, we talk about the magnetic field intensity H. And the magnetic field intensity H is related to the magnetic flux density B by the quantity permeability. This is the constitutive relation, the constitutive relation for a magnetic material. B is equal to mu H. Again, for an isotropic homogeneous material, this is considered to be linear. Now, in previous case, before we came to the PDE, we considered certain laws which hold for the electrostatic fields. And the most important law is the Gauss's law. By analogy, you also have the Gauss's law for magnetism. Divergence of D is equal to rho, but the divergence of B is equal to 0. This is nothing but your second law, second Maxwell's equation, which tells you that divergence of B equal to 0, which means that if you consider the total flux coming out of a closed surface, the total magnetic flux coming out of a closed surface will be 0. So whatever magnetic flux leaves has to come back. Whatever magnetic flux leaves the surface must also re-enter the surface. So the net magnetic flux through any closed surface is 0. The second law that we are interested in is your Ampere's law, which tells you that the curl of H is equal to J. So if you remember, I told you that if you have a fill like this, you need to be told what is the flux density, and that is what you have. Ampere's law tells you that the curl is not 0, the curl of a magnetic field is not 0, and this is specified. So this is what I was meaning, Hitesh. Current is what is the source. Current is not what you are, not the field that you are solving for. Current, when you have a current, current causes the magnetic field. So J is the source quantity. Curl of H is equal to J. Now, if you integrate this over a surface, over the entire surface, curl of H dot ds is equal to integration J dot ds. Integration of J dot ds is nothing but your current. So this gives you the familiar expression for Ampere's law, which tells you that the line integral of H around a closed path is equal to the current traversing the surface bounded by the path. So this is your Ampere's law. So now again, we have put together some relations and some laws, which we can now try and put together. Now remember, we say that if you have a field for which the divergence is 0, and that's exactly the case, divergence is 0. So this is a solenoidal field, and therefore if divergence of B, we are not working with H here, B and H are similar. So if divergence of B is equal to 0, then it should be possible to express B as the curl of an arbitrary vector A. This A is different from the A in the previous slide, where A was used to represent the field itself. Here the field is being represented by B, and A is a second vector quantity. If that is the case, that if B is equal to curl of A is the magnetic vector potential, which you are all familiar with. Now, if you consider B to be a three-dimensional field, Bx, By, Bz, if you take the curl, you will be able to express this as delta divergence A minus del square A. But for a static magnetic field, divergence of A is equal to 0. Remember, A is any vector. When you express B as the curl of a vector A, there is no limitation, there is no constraint on the kind of A you can choose. So you can choose any A, and you will choose an A for which the divergence A is equal to 0. And That is true for a static magnetic field. If you do that, what happens is this term vanishes, and what you're left with is curl of B is equal to minus del square A, which is nothing but, so therefore del square A is equal to minus curl of B, which is nothing but minus mu curl of H. And what is curl of H? We know that curl of H can be expressed as J. And therefore, this is nothing but minus mu J. So therefore, now from this Gauss's law, we have arrived at an equation, which is a differential equation. Del square A is equal to minus mu J. Del square is nothing but your Laplacian. But there is a difference. The difference is this, that A is a vector quantity and J is also a vector quantity. Now, if you look at this equation, it is very similar to the equation that you have been working with for electrostatic fields, except for the fact that A and J are vectors. Now, thinking about the field B. What we have been doing so far is we have been considering only two-dimensional fields. Let us imagine that B is a three-dimensional field. Bx, By, Bz exists, which means Hx, Hy, Hz exists. Why does the B or H exist? Because of the current. The source is the current. The source is the current. Now look at J. If you have a current J, what would be the direction of A? What would be the direction of B? So let us consider current J. Let us imagine current J has three components, Jx, Jy, Jz. What would be the direction of the field due to Jx? I want somebody who does not answer to answer. Ashok.
Yes, ma'am.
If you have a current Jx, what would be the direction of the magnetic field due to Jx?
In the other two directions.
What are the other two directions?
Not able to understand the question now.
Of course, you're able to understand the question. If I gave you current Jx, how would you draw the magnetic field due to Jx? Magnetic field B due to Jx. What is it?
It will be
Yes, you are right.
around. It will be around the x-axis in the circular form. So it will be.
It will be around the x-axis in the circular form. Yes. Now give me a more specific answer.
So it will be in the other two directions of y and z. It will have components in the other two directions.
It will have components. Will it be in one direction? Will it be in two directions? It will be in what? It's a planar field, right?
Yes, ma'am. It's a planar field. It will not have a
in
component
YZ plane.
Yes.
Why don't you speak mathematically? What you're saying is correct. Why don't you speak mathematically? Jx gives rise to a magnetic field which is constrained in the YZ plane. And so B, you will have By, Bz. What will be the direction of the consequent magnetic vector potential A? If you have a field only in the YZ, okay, YZ, only in the YZ plane, what is the direction of the magnetic vector potential A due to it?
It will be in x direction.
It will be in x direction.
Perpendicular to both the.
It will be perpendicular to the YZ plane. So it will have to be in the Z direction, X direction.
X direction.
X direction. So therefore, if you have a current Jx, it will give rise to a magnetic vector potential, which is constrained in the X direction.
Yes, sir.
If you have Jy, it gives rise to a magnetic potential in Y direction.
Y direction.
Therefore, the beauty of this is that even though A is a vector and J is a vector, J is in X, gives rise to B in the other two dimensions, but Jx will only influence Ax, Jy will only influence Ay, Jz will only influence Az. And therefore, even though this is a vector equation, it is possible to break it up into three simultaneous equations. Del square Ax is equal to minus mu Jx, del square Ay equal to minus mu Jy, del square Az is equal to minus mu Jz. And you can solve this equation separately. Once you have solved this equation separately, independent of each other, you have the Ax component, you have the Ay component, you have the Az component, put the three together, and you have the vector field A. So therefore, even though this is a vector equation, all you need to solve three Poisson's equations. So therefore, my question to you is it therefore possible for you to use the MATLAB program that you have already written for electrostatics to solve a magnetostatic fields? Or would you need to make some changes? If you need to make some changes, what changes would you need to make? Darshan, is he here?
Yes, ma'am.
Yeah, tell me. You understood my question, right?
Yes, ma'am. Ma'am, in the electrostatic program, we have one component.
You have one component. So can you not call the program 3 times with Jx, Jy, Jz and independently solve for Ax, Ay, Az?
Yes, ma'am, probably.
Yes, there is no probability about it. You can. So therefore, right now you're in a position already. Remember, I told you that the reason that I spent so much time on the electrostatic fields problem and developing the finite elements method based on the electrostatic field problem is that once you have done that, you actually have done a lot more than you expect. Now, if you want to solve the magnetostatic field, all you need to do is you need to solve these equations 3 times and you will get the 3 different components, put them together and plot the field B. Is this point clear to everybody? There is an additional factor. Let us imagine.
Ma'am, I have a question.
Yes.
Ma'am, in electrostatic field, like del square phi was equals to rho v. So rho v was the boundary condition. So we were knowing
Rho v
the
was not a boundary condition. Rho v was a source function.
I'm sorry, sir. Means it was known to us.
It was known to us. How do we expect to solve a magnetic field if you do not know the current which is causing it?
Ma'am, suppose the condition is given for current. Condition is given for IA, and we have to find Jx, Jy, Jz.
What is given?
Current is given.
Current is
And
given means
if
what?
it is, miss, suppose we have a conductor and current entering from the surface is
Total
given.
current is given.
Total current is given. And because of some situation, the current distribution is non-uniform. Then
That is not a field problem. I'll discuss this with you later. You come to my office.
yes,
That's a separate problem. So yes, you have to know how to set it up as, first you have to set it up as a problem you want to solve. And we are solving for the fields. If you know currents and you want the current distribution, we will have to look at a different scenario. I'll discuss that later with you.
yes.
Now, in this case, what I'm going to say, what was I going to say? Yes. Now, let us imagine that there is no current if J is equal to 0. Can you still have a magnetic field?
Ma'am, yes, sir. If at that point J is 0, then because J is present somewhere in the space,
J is present
it can
nowhere.
have magnetic field.
J is present nowhere.
Then it will be 0.
What will be 0? No magnetic field.
Yes, ma'am. There
No
won't be a
magnetic field without current. Is that what you learned in class 7 or 6? See, the more difficult things you learn, the easier
Ma'am,
things you forget.
but from the Maxwell equation, if del D by del T is non-zero.
I'm asking you a
then
simple question.
yes,
I'm
ma'am.
not asking you about Maxwell's equation.
Yes,
I'm
ma'am.
asking you a simple question, which I may even ask a schoolboy. Answer the question. You know the answer. If there is no current, is it possible to have a magnetic field? By no current, I mean, of course, the DC current or the real kind of current that you talk about. Current that is caused by potential difference between 2 points. Ohmic currents. Have you ever seen any magnetic field anywhere where there was no currents?
Permanent magnet.
Yes, ma'am.
Let me take a poll. How many of you have seen a magnetic field without currents?
Ma'am, permanent magnet.
Where is the poll? I'll take a poll. How does one take a poll? Are Baba, I'm asking you the question. The poll is taking me elsewhere.
Ma'am, yes, ma'am. I have understood. Means if
Yes, ma'am, it
permanent
will.
magnet is there. Ma'am, actually, I was stuck
Answer.
in like
In yes
if
or no?
current if
In the chat box,
ohmic,
everybody give me an answer. Yes or no?
yes, ma'am.
Ashok says yes. Darshan says yes. Everybody says yes. 4. Yes. Except Hitesh, everybody says yes. Hitesh has never heard of permanent magnets. Yes, Hitesh? Where are you hiding now? So if J is equal to 0, you can have a magnetic field which satisfies the equation curl of B is equal to 0. Now, if curl of B is equal to 0, you can no longer have a magnetic vector potential. If curl of B is equal to 0, then B can be expressed as the gradient of a scalar potential. So H is equal to minus grad Vm. And the equation then in this case, del square A is equal to minus mu J becomes del square A is equal to 0, which gives you del square Vm is equal to 0. This is what you have. So therefore, in case of magnetostatic fields, you have two scenarios. In one case, you have a magnetic field. You have a vector field, which is expressed in terms of the vector potential. It is not a problem because in that case, you just need to solve the Laplace of the Poisson's equation in 3 dimensions separately as scalar equation. A scalar equation in X, a scalar equation in Y, a scalar equation in Z. There is 3 resources for magnetic field. Yes, ohmic current, I said, is not present. Varying electric fields, we are not talking about right now because we are considering stationary cases. Yes, permanent magnet, that's the answer. So yes, that is the situation. Or you can have a second situation, which is the second situation is the magnetic field in a permanent, due to a permanent magnet. When you have the magnetic field due to a permanent magnet, you only need to solve Laplace's equation because you're solving for the scalar potential. Okay? So this is the point. I'm going to stop here. I'm out of time. So where we have got to is this, that once we have the means, we have written down a program to solve the electrostatic field problem, we can modify that program very slightly, either to solve for the vector potential or to solve for the scalar magnetic potential. The scalar magnetic potential does not solve the Poisson's equation, solve Laplace's equation. Laplace's equation gives you the scalar magnetic potential, which is only pertinent in the case of permanent magnets. But for magnetic field due to current, you have to solve the vector potential. I will discuss a little bit more about this in the next class, the boundary conditions and etc. I'll discuss tomorrow. I think there are no